In this video, we will be solving a problem involving a cable loaded with concentrated loads. The problem that we will be is somewhat similar to a passboard question. So let's proceed. So cable ABCD as shown on the right side is divided into 3 segments and loaded as shown. So first question, determine the tension in segment AC. Second question, it is asked here that we should determine the tension in segment CD. And in third question, we will be asked to determine the tension in segment BD. The last question asks us here to determine the total length in feet of the cable. So let's solve question number 1. Let us determine tension in segment AC. First thing we need to do here is to draw the free body diagram of the whole structure. But if I would to show directly the FB diagram here, you would be noticing that the resultant reaction at A is denoted as TAC, which is equivalent to the tension of segment AC. Likewise, you would also notice that the resultant reaction at B is denoted as TBD, which is equal to the tension of segment BD. Why did I say so? So let's isolate joint A and let us draw the free body diagram of joint A. So at joint A, we have here the horizontal reaction at A, and I denote it here as AH, wherein the subscript H pertains to horizontal. Likewise, we have also here the vertical reaction at A, which I denote here as AB, wherein the subscript B here pertains to vertical. And other force that will be involved at joint A is the tension segment AC. And I denote this tension of the segment as TAC. To basically analyze a joint involving forces that are not horizontal and vertical, it is simpler to analyze it when we convert those inclined or those forces that are not horizontal and vertical on their components. So let's say this is the horizontal component of the tension AC, which I denote here as TACH. Again, if you would to see notations here that has a subscript of H, those pertains to horizontal components. Likewise, we also have here the vertical component of the reaction, which I denote here as TACV. Again, those notations of forces which have a subscript of B, those pertains to vertical components. So if we would to analyze joint A, let's try to sum forces along the horizontal direction. If you would to look at our free body diagram of joint A, there are only 2 horizontal forces that are involved, which is AH and TACH. Again, for joint A to be in equilibrium, these forces should contradict each other, and that would only happen if AH is equal to TACH. If their value is equal and they act opposite on the directions that we are considering, then point A would be in equilibrium if AH and TACH are equal. Now, let's consider summing vertical forces, and the vertical forces included only at joint A is AB, the vertical component of the reaction at A, and TACB, the vertical component of the tension of segment AC, the segment that is connected at joint A. Again, in order for joint A to be in equilibrium, the sum of all the vertical forces must be 0. Since there are only 2 involved vertical forces and they act in opposite direction, we will only attain the equilibrium state if AB and TACB are equal. they must be equal in magnitude and they act on opposite direction. What do I mean by that? AV should be equal to ACB in order for point A to be in equilibrium. Now, AH is equivalent to the horizontal component of the tension of segment AC, the segment that is connected at A. Likewise, the vertical reaction at A is also equivalent to the vertical reaction of the tension of the segment connected at A. These only conclude that the resultant reaction at A would be equal to the tension of the segment connected to it. But I have to reiterate something here. The concept that I just said would only be applicable if there is no external forces that acts at joint A. What do I mean by that? If there would be a horizontal force that would act at A, again, we will need to consider another equation, since if we would to summate horizontal forces, TACH and AH will be involved in the external forces. We shall need another equation pertaining or involving AH and TACH to compute for their values. Again, for cases wherein the joint where the support is located does not experience or imposed by external forces, the resultant of the reaction at that point will be equal to the tension of the segment connected to it. That's the principle why I would to show you now the action of the whole structure. You would noticing that the resultant of the action at A would be equal to the tension of the segment that is connected to it, which is segment AC, as well as at joint B. Let's draw the free body diagram of the whole structure. So we have here the resultant reaction of joint A, and let's say this is the angle of the resultant reaction at joint A with respect to the horizontal. But in analyzing system, it is way better to convert those forces that are not vertical and horizontal onto their components. So let's say this is the horizontal reaction at A and this is the vertical reaction at A. We have also here the resultant reaction at joint B, and let's say this is the angle with respect to horizontal of the resultant reaction at joint B. And let us again convert the resultant reaction at B onto its components. So let's say this is its horizontal component and this is its vertical component. Now that we've already drawn the free body diagram of the whole structure, our strategy here is to compute for the horizontal and vertical reaction at A, because this is also the components of the tension of segment AC. That is why if we can compute for the horizontal and the vertical component of the reaction at joint A, we can now basically get the tension of segment AC. Basically, we need two equations here involving TACH and TACV. Saan ba manggagaling yung mga equations na yan? So basically, those equations will come from the equations equilibrium. If we would to pick one of those equations, the other unknowns would be eliminated. And basically, what we can use in the equation equilibrium would be the summation of moment. Why? Because if we would to take a moment on a point wherein some of the unknowns that we are not after for can be eliminated, and those unknowns only that we are after for will have a moment. And if you would to investigate the whole structure, the first equation that we can come up with is an equation when we summate moment at B. Why? We would to summate moment at B, the unknowns at that point, specifically the horizontal reaction and vertical reaction at B, would have a zero moment value when we take moment about B. And the remaining forces would be the external forces as well as the unknowns that we are after for. Okay? So let's take a moment about B wherein assuming that clockwise moments are positive. So let us first take the moment of TACH about B. If we would to look at it, TACH would produce a clockwise moment about B. So TACH multiplied by its moment arm, which is 2. Now let's take the moment of the vertical reaction at A about B. If we would to look at here again, TACB would produce a clockwise moment about B. That's why we have here TACB multiplied its moment arm, which is the sum of 3, 4, and 3, which is basically equal to 10. The remaining forces that have a moment value about B are the external forces. So let's take the moment of the 80 pounds force here. And if you would to look at here, the 80 pounds force here would produce a counterclockwise moment. That's why it is associated with a negative sign here. And its moment arm from joint B would be 4 plus 3, which is basically equal to 7. Now, we need to take the moment of the other external force, which is the 50 pounds. So if we would to look at here again, 50 pound force would generate a counterclockwise moment about B. That's why we have here negative 50 multiplied by its moment arm about B, which is 3, equal to 0. So let's simplify this equation. These terms that involves unknown variables will be retained on this side, and these terms shall be simplified and be transformed on the other side, and we will come up with a value of 710. And again, this value is the value when we perform the present operation of these terms involved here and we transfer it on the other side. Now, let's call this equation as equation 1. Now that we've already come up with one equation, we need another equation involving these two unknowns here. And you might say that there is still two remaining equations from the available equations of equilibrium, which are the summation of forces along the horizontal and vertical direction. But if we were to use those equations of equilibrium, considering the whole structure, we will be involving the unknown reactions at B, and we don't like that one. We only need an equation that involves the reactions or component reactions at A. So basically, summation of moment will be the equation that we will be using again to generate the another equation that we need. But by how? By method of section. There are different locations here where we can pass a cutting plane, and this location is the segments themselves. So let's analyze possible location where we can pass a cutting section. So let's try to explore possible location where we can pass cutting section. So let's first pass a cutting section AA on segment AC, and let's consider the sign where it includes joint A. Since we pause a cutting section at segment AC, it would be exposed here the tension of the segment itself, which is TAC also. However, we would use the equations of equilibrium if here we will not produce any equation since the resultant reaction at A and this tension of the segment AC are equal. So let's proceed considering the other possible location where we can pass a cutting plane. So other location here is to pass a cutting plane on CD, and let's denote that cutting plane as BB, and let's consider the segment which includes joint A. Since we pass a cutting plane on segment CD, it will expose the tension of the segment cut, and which is denoted as TCD. From this free body diagram, if we would to apply the two equations of equilibrium pertaining to summating forces along the horizontal and vertical reaction, the equation form will involve another unknown, which is tension TCDE, and we don't want that one. What we are after here is to produce an equation that would only involve the unknown, which are the horizontal and vertical reactions at joint A. And we can only produce that equation if we would to use again the equation of equilibrium pertaining to summating of moment. And from this free body diagram, there are two prepared points where we can take moment. These points are point C and D. Why? If you would to look at the line of action of tension TCD, it would pass through these points. Meaning, if we would to take moments about point C and point D, TCD will now have a moment value about those points. But in choosing which of these 2 points where we will be taking moment, is that our consideration is that the moment arms of those involved forces should be known. If you would inspect, if we would to take moment about C, the moment arm of TACH is unknown, and there is no way where we can solve for that moment arm. So the remaining point is the prepared point where will we be taking moment, and that point is point D. Why? Let's again investigate or inspect the moment arm of those forces that are involved in taking moment. So let's first look at the moment arm of TACH. The moment arm of TACH about D would be this vertical dimension here, and this basically computed from the known or given dimensions. Look at this one. The vertical distance between points B and D is 5, and the vertical distance between B and A is 2. So basically, if this distance here, which is 5 feet, if it's subtracted by 2 feet, then we will get this distance here. So basically, that would be equal to 3 feet. If you would to look at the vertical reaction at A, its moment arm about D would only be the sum of 3 feet plus 4 feet. And again, the other loads that are involved when we will be taking moment about D is the external force, which is the 80 pounds, and its moment arm about D is known to be 4 feet. And those forces that will be involved when we would to take about D have their moment arms about that point to be known. So let's take a moment about D, assuming that clockwise moments are positive. So let's first take the moment of the horizontal reaction at joint A. The horizontal reaction at A would produce a counterclockwise moment about D. So we have here negative TACH multiplied by its moment arm, which is equal to 3 feet. Now, the vertical reaction at joint A, it would produce a clockwise moment about D. So we have here plus TACV multiplied by its moment arm, which is equal to 3 plus 4, which is equal to 7. And the other force that is involved is the external force 80 pounds. This force will produce a counterclockwise moment about point D. So we will have here negative 80 multiplied by its moment arm, which is equal to 4 feet, then equal to 0. Again, like what we've done with equation 1, let's retain these terms with unknown variables, and those terms that we can simplify will be simplified and be transferred to the other side. So we have here negative TACH times 3 plus TACV times 7, and we should perform the present operation here and transfer the result from the other side. So we will get here negative 320, and let's denote this equation as our equation 2. Now that we've produced 2 equations involving the 2 unknowns that we are looking for, so we can now basically compute for the tension in segment AC. So this is the summary of the equations that we've generated. So using the equation solver of our calculator, we basically compute the value of TACH to be 40.2273 and the vertical component of the reaction at joint A to be 62.9545. So the resultant reaction at A, which is also equivalent to the tension in segment AC, which is the one that being asked in question number 1, would be get by taking the resultant of the components, and that can be done by taking the square root of the sum of the squares of the component. So by substituting these components in this given formula, we will get the value of the tension in segment AC to be 74.7095 pounds. And based from the choices, our answer for number 1 would be letter C. Let's proceed with question number 2. In this item, we are asked here to determine the tension in segment CD. Now, here's the principle when it comes to problems involving cable that are loaded with concentrated load. We can basically apply here method of joints. So the primary consideration in choosing which point to analyze shall include the segment that we are looking for its tension. So the segment that is being asked in this item is the segment CD. So the points that are preferably we can analyze in order to compute for the tension of that segment would be joints C and D. But the second primary consideration in choosing which joint to analyze would be the connected segments there. So if we would to analyze a joint, if the segments connected at that joints are not vertical or horizontal, so technically the unknown segment of that joint shall be limited to one only. Why? Because when we are using the method of joints, there are two applicable equations of equilibrium that we can apply. That is the summation of forces along horizontal and vertical. Meaning, if the unknown segment connected at that joint is not horizontal or vertical, then it would have a horizontal and vertical component, and that's the two unknown that we can solve by using the aforementioned equations of equilibrium. So if we would to consider joint D here, the segments that are connected there is segment CD and BD. We are looking for the tension in CD, but the tension in BD is unknown. So basically, joint D would be eliminated on our choices of joints that it is preferable for us to analyze in order to compute for tension in segment CD. So what we are left here is to consider joint C. So let's analyze joint C. This cut section here is segment AC, and let's say that this is theta angle AC, which is the angle that TAC makes with the horizontal. So for ease in computation, for those forces that are acting on the joint that is being considered is not horizontal and vertical shall be converted onto their component. So let's say this is the horizontal component of TAC, which has a value of 40.2273 pounds. This value was computed from the previous item, and this is its vertical component, which has a value of 62.9545 pounds. This value was derived from the previous equation. And the remaining segment here is segment CD. And let's say also that this is theta CD, which is the angle that TCD makes with the horizontal. And again, let's convert this tension into its component. Let's say that this is its horizontal component, denoted here as TCDH, and this is its vertical component, which is denoted here as TCDV. As mentioned earlier, when we are using the method of joints, the only applicable equations of equilibrium that we can apply would be the summation of forces along the horizontal and vertical direction. So let's consider first the summation of forces along the horizontal direction, considering that those forces acting to the right to be positive. So the involved forces would be first the horizontal component of the tension TCD, which is TCDH, and it is associated with a positive, which is invisible here, positive sign, because it is acting to the right. And the remaining force that would be involved here is the horizontal component of the tension AC. So that would be negative TACH. Again, this negative sign associated with the horizontal component of the tension in segment AC is pertaining to the direction of that force itself. It is acting to the left, that's why it is associated with the negative sign. If you would to look at joint C, there will no longer horizontal forces that would be involved in this equation. So that would follow now equal to 0. So let's substitute the values of those variables known in this equation, and that would be TCDH minus 40.2273, the value of the horizontal component of the tension in segment AC. So basically, the horizontal component of the tension in segment CD would be equal to 40.2273 pounds. Now, let's take summation of forces along the vertical direction, assuming that those forces acting upward would be positive. So the primary forces that would be involved here would be the vertical component of tension CD, and it is acting upward. That's why we have here positive TCDV. And another force that is involved here would be the vertical component of the tension in segment AC, which is TACV, and again this force is acting upward. That's why we have here plus TACV. If we would to look at joint C, there is one left vertical force that will be involved, and that is the external force 80 pounds. This external force is acting downward, so that's why we will have here negative 80 equal to 0. So if we would to substitute the values of the variables known in this equation, we will come up with this equation: TCDV plus the value of TACB, which is 62.9545 minus 80, and from this equation we can now basically compute for the vertical component of the tension in segment CD, which is equivalent to 17.0455 pounds. So this is the summary of the components of the tension in segment CD. So to compute for the resultant tension in segment CD, we will basically compute for the square root of the sum of the squares of its components. So substituting the values in this given equation here, we will yield for the value of the tension in segment CD, which is equal to 43.6896 pounds. And from the given choices, our answer would be letter B. Let's now proceed computing question number 3. And in this item, we are asked here to compute for the tension in segment BD. If you would to look at the FBD of the whole structure, there are various ways on how to compute for the tension of this segment. You can compute for the reaction at B, since, as discussed earlier, the resultant reaction at B is equal to the tension of the segment connected to it, provided that there are no other external loads acting on that joint. But in this video, what I will be presenting to you would be by using the method of joint. So I would be considering here joint D. If I were to consider this joint, the connected segments here would be CD, and its tension is already known, as computed from the previous question. And the remaining segment connected to it is segment BD, which is the segment that we are after for in this item. And since in this joint there is only one segment that is unknown, that is why the method of joint is applicable when we would to consider joint D. So let's analyze joint D. This segment is segment CD, and let's say this is theta CD, which is the angle that tension CD makes with the horizontal. And again, for ease in computation, for these forces like tension CD, which are inclined and not horizontal and vertical, is preferable to be converted into their component. So this is its horizontal component with the value of 40.2273 pounds, and this is its vertical component with the value of 17.0455 pounds. And this segment here is segment BD, and the tension there is denoted as TBD. And likewise, let's say this is theta BD, which is the angle that tension BD makes with the horizontal. Likewise, we would to convert this tension into its component, and let's say this is its horizontal component, which is denoted here as TBDH, and let's say this it is its vertical component, which is denoted here as TBDB. Again, the equations applicable when we are using method of joints would be summation of forces along the horizontal and vertical direction. So let's first consider summation of forces along horizontal, considering that those forces acting to the right to be positive. So the load or force that will be involved here would be the horizontal component of the tension BD, which is TBDH, and it is acting to the right. That's why it is positive. Another force that would be involved in the summation of forces along the considered direction would be the horizontal component of tension CD. That force is acting to the left. That's why we will have here minus TCDH. And if you would to look at joint D, there will be no more horizontal forces that will be involved in this equation. So this equation will be followed equal to 0. So let's substitute the values of the variables that are known. So TVDH minus the value of TCDH, which is 40.2273. So basically, the horizontal component of tension BD would be 40.2273 pounds. Now, let's take summation of forces along the vertical direction, considering that forces acting upward to be positive. So from joint A, the force that would be involved would be the vertical component of tension BD, and this component is acting upward. That's why we have here positive TBDV. And another force that will be involved in this equation would be the vertical component of tension CD, and tension CDV, or the vertical component of tension CD, is acting downward. So we have here negative TCDV. And if we would to look at joint D again, there is another one force that will be involved in the equation, and that is the external force, which is the 50 pound. This force is acting downwards. That's why we will have here minus 50 equal to 0. Now, let's try to substitute the values of the variables in these equations that are known. So TVDV minus the value of the vertical component of the tension of segment CD, which is 17.0455, minus the external force, which is 50. And if we were to simplify this one, we basically get the vertical component of the tension of segment BD to be equal to 67.0455 pounds. So here's the summary of the components of the tension in segment BD. So to basically compute for the resultant tension, we will basically compute for the square root of the sum of the squares of each component. So substituting the values of the components onto this given equation, we will yield the tension in segment BD to be 78.1878 pounds. And from the choices, our answer would be letter A. Let's proceed answering the last question for this problem. In here, we are asked to determine for the total length of the cable. So if we would look on the figure, and if we would project horizontal and vertical lines from the joints, we will basically form here right triangles. And if you would observe these right triangles, their hypotenuse sides represent the segments of the cable. So if we can compute for those sides and add it up, the result would be the total length of the cable. So first, may I denote this side of this triangle to be Y and this side of this triangle to be Z. So our objective first here is to compute for the values of these variables. But first, may I transform this component representation of the resultant reaction at joint A into its triangle force representation. If we would to do that, we will be coming up with this representation with this component as the horizontal and this component as the vertical. From this representation, we again form a right triangle. So let me first present here the summary of the components of the resultant reaction, or basically the tension in segment AC. This force representation of the segment AC is collinear to this physical representation of segment AC. So if these are collinears, if this is theta AC, this would also be theta AC. And if two triangles have equal angles, then these triangles are considered to be similar triangle. And if we have two similar triangles, we can basically use the concept of ratio and proportion. So considering the triangle force representation here, TACV is to TACH equal to, from this triangle, Y is to 3. So basically, ang ginawa natin dito is that we basically compute for the value of tan AC from this triangle. Tan AC from the triangle force representation would be opposite, which is TACV, over the adjacent, which is TACH, equal to the tan value of theta AC from this triangle. So tan theta AC would be equal to opposite, which is Y, over the adjacent, which is 3. Now let's substitute the known values of the variables here. So TACV is 62.9545 over TACH, which is 40.2273, equals to Y over 3. And from this equation, we can now basically compute for the value of Y, which is equal to 4.6949 feet. So let's solve the value of the variable Z. So in here, the value of Z can be computed by adding this side of this triangle and this given dimension here and subtract it with this dimension, and that's basically the value of Z. Again, if we would to add this side of this triangle plus 2 feet and subtract it by 5, we will yield for the value of Z, which is equal to 1.6949. Now that we've already computed for the dimensions of the formed right triangles, we can now basically compute for the total length of the cable. In here, we've denoted the total length of the cable as LT. So by using the Pythagorean theorem, we can now compute for the different hypotenuse of the right triangle form. So for segment AC, that is equal to the square root of 4.6949 squared plus 3 squared. Again, this term is the length of segment AC plus square root of 1.6949 squared plus 4 squared. This term represents the length of segment CD plus 5 squared plus 3 squared, and take it the square root, that would be the length of segment BD. So if we were to perform the operations here, we will get the total length of cable to be 15.7468. So from the given choices, our answer would be C, and that would be the closest to what we've yielded. And that's all. I hope that you've learned something. Thank you for watching, and hope to see you soon on next videos.